Hey guys, welcome back to my channel. This is day 39 of my algorithm challenge. We're already past the 1/3 mark of the 100 day, and I'm very satisfied with how our progress is. And thank you guys for keep tuning in. You guys' support mean a lot to me. Today we're going to go into dynamic programming. We have finished backtracking. Finished as in we have looked at the basics of it. And like I always say, we're going to go back to all the templates that we have done and try to solve more questions after we go through all the theories. And this dynamic programming is the last bit of theory, and it's often called as the hardest and trickiest. This makes it not less common in interviews, but the thing is, if this kind of problem comes up, so dynamic programming comes up, it will be kind of impossible to find out the solution without knowing how to solve this. So it is best to have a look at it. I'm going to share my screen. Uh, 1 second. Yes. So when you search dynamic programming on Wikipedia, it's basically optimization method and algorithmic paradigm. Um, It refers to simplifying a complicated problem by breaking it down to simpler subproblems in a recursive manner. So basically, it's a optimized recursion. So it is the variant of depth first search, which also used um, the recursive method and also backtracking as well. And finally, we have the dynamic programming. Um, so what makes it a dynamic programming? Um, Usually there's this recursive function called DP that returns the answer to the original problem as the arguments you passed it was the input. And the arguments that you put in is usually called a state. So state, this is a very important term in dynamic programming. So what is a state? Um, State refers to a set of variables that can fully describe a scenario. So when we look at the tree, every recursive call to depth first search, for example, took node, and that node is called the state. There are different types of state. Um, for instance, there could be an index along the input string. So index string I. So I could be like a state. So this is like the most common state variable, and it is usually the state variable in all the interview problems. Uh, and in a Fibonacci sequence, for instance, if you look at the I, so index refers to the current Fibonacci number. Um, so this I is very important. Um, Also, this term memoization and tabulation is the core of DP. So let's look at memoization first. Station. Uh, Difference between DFS and DP is that dynamic programming allows the state, this index, to be repeated. So for instance, if you look at the Fibonacci sequence, so we can start from usually there's 1 second. Yeah, this is a Fibonacci sequence. So if n is 0, we return 0, n is 1. I think this should be 1. We also return 1, and then we return Fibonacci n minus 1, n minus 2. So we add up the sum of the two numbers that was before the number. And we keep adding and adding to make a Fibonacci sequence. And every state is an index. And there are times when these numbers are repeated. For instance, if we are to find a Fibonacci sequence of 5, we will only always have a children node of 2 children node, right? Because we're gonna find the Fibonacci of n-1 and Fibonacci of n-2 as a recursive call. So this could be 3 and 4, and this will also divide into 2 and 1, and this will become 3 and 2. And from here, we can already see that this 3 is duplicated here and here. This 2 is also duplicated here and here of child node of 3 and 4. So while this repeats and repeats, of course, in a lower computation, lower Fibonacci sequence like this, it will not have that much effect. But when we look at much higher numbers, this number can rise exponentially and rise the effort to do a computation exponentially as well alongside. So it is important to try to remove these duplicates, and to do that we use this memoization. Yes. So what is a memoization? How do we do it? So for a given value, we cache that value usually in a hash map. So what is a caching? Caching is a term usually used in operating system. So we store it in some kind of in-memory, and then we bring it back up when we need it. So we don't put it back into the long-term storage. We usually keep it in the in-memory, and then we recall it as soon as we use it. So it is very effective when we need it right away. So think of it as a short-term memory. So when we, like I said, we find something for a given state, and then we cache that value. And since we know that that value is in a hash map, we can avoid it, since we're going to keep on comparing that. And yeah, in some ways, you can see this as a backtracking, in a sense that backtracking also doesn't allow duplicates. But in this sense, it is using the hash map. Let's see. So what will be the time complexity? In a Fibonacci sequence like this, this is not using any memoization nor tabulation. We're going to go into tabulation, but tabulation is also part of DP. So this is just a plain Fibonacci sequence without any dynamic programming. And this will have the time complexity of 2 to the power of n, because every node has a child node of 2 to the power of n mar. But if you use the dynamic programming, such as memoization, this is the one that uses memoization. As you can see, there's an empty hash map, and you store the value in a hash map. And then if the n is in memo, so memoization, we return that state. And that's how we avoid having duplicates. It will improve the time complexity to n. So that's really, really effective and really a meaningful improvement. Now, since we already got into memoization, we're going to talk about top-down and bottom-up approach to dynamic programming. It is named as such because we start from the top and move down towards the base case in a memoization using top-down approach. So when you're using memoization, it's a top-down approach. When you're using bottom-up approach, that's called using tabulation. So for instance, in memoization, we started by calling Fibonacci Mn, and we moved down with recursion until we reach the base case, which is it's not here, but f0 and f1. It is here, yeah. If when n is 0 and n is 1, this is the base case, right? Where we stop the Fibonacci sequence. When we use the tabulation, this is the method of using tabulation. We start from the bottom case, so that is when array is filled with n plus 1, and then move our way to the larger problems. So we use the full for loop here, and then we keep on iterating, yeah, to fill it up. And yeah, this is called a bottom-up approach. And there are three characteristics of bottom-up approach tabulation. First is that it is an iterative process. So the function iteratively calculates the Fibonacci numbers from smallest to the largest rather than starting with the largest and working backward, which I already talked about. Second characteristic is that there is no recursion like top-down approach. This makes it sometimes harder to think of it, and then it's harder to yeah, harder to come up with it. It uses a for loop usually instead, which avoids the overhead of recursive calls and potential stack overflow issues. Lastly, there's a bottom-up approach usually has a better space complexity. So it uses a fixed amount of state space. In this case, it is the array that we are using as the space. So this is more effective in terms of space complexity compared to the recursive call stack that we have used in the top-down approach. And this recursive call stack can sometimes make the stack overflow, which is a problem, right? Now, yeah, just to briefly explain here, how it works is at each iteration, it calculates the ith Fibonacci number, and by adding the two preceding Fibonacci numbers and I minus 1, array I minus 1, this is state. You can see that it uses state again, I minus 2 state from array, and it stores the result in array I. And then after that, it returns the array n. Yeah. Now that we know the basics of the dynamic programming, there are problems that the problems that use dynamic programming have two main characteristics. First is that characteristics of DP problems. So problem will be asking you for an optimal value of something. So like, for example, the maximum cost of, or what is the longest possible way to do something. Also, the second characteristic is that at each step, so at each state, you need to make a decision, and decision affect future decision. So this is similar to backtracking as well, or greedy algorithms, in a sense that you have to find the optimal decision at every state. Yeah, it could be really simple, like picking between two elements. Yeah. Okay, lastly, to end this theory, the time and space complexity of DP algorithms is really simple. You just times the n possible states, so n possible states times the the amount of computation done at each step. So that's F. So the time complexity is NF. The space complexity is ON. So um, if we are doing bottom up, the array we use for tabulation is the same size as the hash map, the number of states. So that is our space complexity. So this is fixed. But like I said, for top-down approach, it is a recursive call that defines the space complexity, and it can be sometimes bigger than the bottom-up approach. But it is just the difference is just the way of approaching the problem. As a whole, it is the same dynamic programming approach. So keep that in mind. Yeah. So that was it. Tomorrow we're going to look at the general template of dynamic programming, the one that we can use in most of the questions. You usually have to use the memoization and state. So keep that in mind. We're going to look at it tomorrow with a sample question. And yeah, I'm excited to start this chapter. Hope you guys are as well. And if you guys have any comments, let me down below. Thank you guys all for listening, and see you guys tomorrow.